Hello, my name is Danesh Shamsi. I'm in lab section M07, and this is my video lab report for the physics of extreme sports 2. The overall objective of this lab was to analyze the motion and energy of a mass and spring system in 2 dimensions. I was provided with a video that allowed me to analyze the motion of a mass and spring system in 2 dimensions. By uploading the video to Tracker, I was able to obtain data concerning the time, the x position of the mass on the spring, and the y position of the mass. I was able to do this by using the calibration stick tool and setting the equilibrium length of the spring with the mass equal to 0.7 meters. The x and y position data that was obtained from the Tracker software was uploaded into Excel, and a .csv file was created in order to model this motion computationally in Visual Python. Spring mass system in 2 dimensions. It is necessary to enter the known values so the computational model can accurately model the motion that was displayed in the video. It is known that the mass of the weight was 0.402 kilograms. And using Hooke's law in a previous in-class lab, we were able to determine that the K value was 6.96. This is the spring constant. Using this known spring constant value, we were able to determine that the relaxed length of the spring was 0.1334 meters. Now, using the data obtained from Tracker in our .csv file, we uploaded it right here so it can be modeled alongside the computational model. Now, as I run my code, you should note that the blue ball represents the motion based off of what was obtained in Tracker, while the orange ball represents the computational model. You can see right here that they are following the same path very accurately, but as time progresses they seem to get a bit off track. This will be discussed later. From this, we were able to come up with 2 graphs, being a x position versus time graph and a y position versus time graph. Here we can calculate the period with both respect to x and respect to y. Now, it should be noted that the simulated period is equal, and with respect to y, was 1.5 seconds, and with concern to the actual data was 1.54 seconds. The simulated period with respect to x was 1.6351 seconds, while the actual data provided 1.6081 seconds. Next, the spring potential energy was graphed with respect to time using Visual Python. This spring was assumed to be part of the system along with the mass. Using the knowledge that the change in the spring potential energy is equal to the work done by the spring, the graph was created. The y-axis represents the change in potential energy. Now, it can be seen that as the spring approaches its equilibrium length, the spring potential energy moves towards 0 as it bounces up and down. Now, there were 3 what does it mean questions. The first one essentially asks to compare the period of oscillation with both respect to x and y. Now, it can easily be seen that the period of oscillations were indeed different when it comes to the position data concerning the x and the y. It can also be seen right here from the numerical values themselves. This is because the vertical and horizontal periods of oscillation are completely independent of each other. This can be likened unto much how velocity in the x and y direction for projectiles are independent. The second what does it mean question asked me to determine the work done by the surroundings and if the energy principle was indeed satisfied. Now, in Visual Python, I plotted the change in kinetic energy, potential energy due to gravity, potential energy due to the spring, and the sum of all these potential energies. Those were respectively red, green, and blue, while the sum is equal to yellow. Now, you can see that the total amount of work, the sum, is done by the surroundings is equal to 0. This is because no work is being done into the system, and no energy is being lost due to friction. The energy principle is satisfied because the sum of the change in energy in the system is 0, and the work done to the surroundings is equal to 0. This can be seen in the model. The final question asks how changing the origin of the mass changes the physics of the system and the energy plots. When the origin is changed, a new graph was formed. It can be seen that the numerical values of the changes in certain types of energy were indeed altered numerically. This is because the gravitational potential and spring potential energy depend on values such as distance of interacting masses. However, I believe the actual physics of the system does not change because the energy plots maintain the same form and the bouncing mass behaves in an extremely similar manner to the first model. And the overall change in energy is equal to 0.